We have discussed three types of AM modulations: double sideband suppressed carrier AM signals, conventional AM signals, and single sideband AM signals. For the double sideband suppressed carrier, and this is a modulated signal, we multiply the magnitude of the carrier by the message. And this is a diagram. This is a AMT message, and this is a carrier. This is a multiplier, and we generate the modulated signal. In time domain, we can see here if I have MT in this shape, the magnitude of the modulated signal should change with the shape of, for the spectrum of the modulated signal, we will move the spectrum of the message to FC and minus FC. The magnitude is scaled by half AC. For example, at this point, MF has magnitude 2 and AC is here and half AC. So therefore, the magnitude after shifting to FC and minus FC, the magnitude here become AC. We can see the bandwidth of the modulated signal is 2W, and the carrier is suppressed. There's no carrier transmitted in the modulated signal unless there is a DC component in the message. This component of the carrier is due to the DC component in the message. The power in the modulated signal for the DSP-SS signals is half AC squared multiplied by the power content in the message. To demodulate the DSP-SC signal at the receiver, we multiply the cosine signal with the same carrier frequency. Ideally, we want the phase offset to be 0. And once this offset phi equals to 90 degrees, we cannot recover the message signal at the receiver. So we multiply by this cosine signal, pass through the low-pass filter, we obtain a scaled version of the message. For the conventional AM, we need to understand the concept of overmodulation. Overmodulation occurs when the envelope of the modulated signal, which means the positive portion of the envelope, does not have the same shape of the message. In this case, overmodulation will occur. For conventional AM, we have to make sure that overmodulation does not occur. The conventional AM is achieved by multiplying the magnitude of the carrier by this portion. This portion is 1 plus small a MNT. MNT is a normalized message. You take the MT scaled by the maximum absolute value of MT. Small a is modulation index, is in between 0 and 1. If we design AM signal this way, overmodulation will not occur because A is less than 1, MNT, this will be less than 1 and greater than minus 1. So therefore, there's a 1 here. We can be assured this portion, this whole portion in the green highlighted, is greater than 0. So therefore, overmodulation does not occur. The spectrum of the conventional AM contains two parts. The first part is related with the message, which is normalized. And we can see this portion is DSP-SC because the magnitude is multiplied by the message. So the message here is small a multiplied by MNT. And the second portion of the modulated signal for a conventional AM is the carrier signal itself. So therefore, if we take Fourier transform in this first portion is DSP-SC signal, that's the spectrum using modulation property. And the second portion is the cosine signal of the carrier. We have two specs at FC and minus FC. This is a spectrum. We can see conventional AM does not suppress carrier because there is a carrier transmitted here. And this carrier is not due to the DC component of the signal. It is transmitted here. We can see the bandwidth of the modulated signal for conventional AM is also 2W, so it's called conventional double-side AM signal. The power for the conventional AM modulated signal is half AC squared. This portion is related to the power transmit the carrier, and plus this portion AC squared multiplied by A squared and PMN. And PMN, that's the power contained in the normalized message. So this portion is the power spent in transmitting the message. And we can say conventional AM is not as power efficient as conventional AM because the carrier is transmitted. The receiver for the conventional AM can be achieved for a simple circuit contained with RC circuit and the diode. So this circuit is very, very inexpensive, very cost effective. And this is the advantage for transmitting carrier at the transmitter for conventional AM. For the single sideband AM signals, we want to transmit either the upper sideband signal or the lower sideband signal. If we want to transmit the upper sideband signal, the spectrum of the modulated signal will look like this. This is the upper sideband AM signal using the upper sideband. Implementation of single sideband, we can use the bandpass filter, but we need to require the bandpass filter to be ideal, which is hardly achievable in practical systems. The upper sideband modulated signals can be implemented using the Hilbert transform. So this will achieve the upper sideband modulation. If we want to have the lower sideband modulation, the lower sideband, we change the sign of this Hilbert transform term. So to summarize AM signals, we talk about DSBS signals, conventional AM, and SSB signals, single sideband. And VSB, that is the scheme used in television broadcasting systems. The bandwidth of VSB is in between single sideband and double sideband. And for each modulation, we need to know the time domain expression. How do we modulate the signal? We want to know the spectrum of the modulated signal, the bandwidth of the modulated signal, and the power contained in the modulated signal. So those are 4 perspectives for each modulation we need to know. The spectrum and the power are very important in communication systems. And here, that's the summary for DSBSC AM, for conventional AM, for single sideband AM, we look at time domain, frequency domain, the bandwidth, and the power as the 4 perspective for each modulation scheme.